this lab, we will investigate the reaction between the crystal violet cation, structure on the left, and sodium hydroxide. Our goal is to use a spectrophotometric approach to determine the order of the reaction with respect to the crystal violet cation. This molecular cation lends itself well to this sort of analysis. 3-dimethylaminobenzene rings chemically bonded to one carbocation results in the structure absorbing visible light at a wavelength max of 565 nanometers. The visible wavelengths not absorbed are reflected and result in a purple-colored aqueous solution. Through Beer's law, the absorbance of the crystal violet cation aqueous solution can be related to its concentration. Given that the product of this reaction is colorless, i.e. does not absorb visible light, we can monitor the progress of the reaction by measuring the decrease of absorbance at 565 nanometers as a function of time. While it is helpful to be aware of the complete molecular structure of the crystal violet cation, this chemical reaction is often represented in an abbreviated form as shown here. Cv plus is the purple-colored crystal violet cation, and CvOH is the colorless product. The general rate law for this reaction is written as follows. While our experimental approach can easily be used to find the order of the reaction with respect to the hydroxide ion, we are given a head start and told that this value, corresponding to the exponent n, is equal to 1. This tells us that the concentration of the hydroxide ion does indeed affect the rate of reaction. If we, however, set the hydroxide concentration to be 1,000 times larger than the concentration of the crystal violet ion, then the hydroxide concentration will essentially remain constant over the course of the experiment. Therefore, only the change in concentration of the crystal violet cation as it is consumed will affect the rate. A simplified rate law can be written where K prime is a pseudo-rate constant and is equivalent to the actual rate constant multiplied by the hydroxide concentration. Our goal in this experiment will be to produce an absorbance versus time graph which shows the consumption of the crystal violet cation. Using Beer's law, the absorbance can be converted to the concentration of the crystal violet cation. 3 related graphs can then be produced in Excel. Concentration versus time, ln of concentration versus time, and 1 over concentration versus time. The graph, which shows a linear relationship, will correspond to the order of the reaction with respect to the crystal violet. Therefore, this approach will allow us to determine the exponent m. The experimental setup is shown in this diagram. 10 milliliters of 2.0 times 10 to the negative 5 molar crystal violet solution is added to a beaker. The temperature is recorded. The reaction is initiated by adding 10 mils of 0.1 molar NaOH. A cuvette is rinsed once and then filled with the reaction mixture. It is quickly transferred to the colorimeter. Continuous absorbance readings as a function of time are recorded on the LabQuest 2 screen. A few words about this experimental setup before we turn to the physical lab and watch Scott perform the experiment. Scott will use a colorimeter instead of a spectrophotometer. Both instruments measure the degree to which a solution absorbs a beam of light at a set wavelength. A spectrophotometer, however, is generally more expensive and uses a diffraction grating to set any wavelength in the visible spectrum. A colorimeter, on the other hand, uses filters to select a wavelength, and this particular model is limited to 4 prescribed wavelengths. Fortunately, one of the prescribed wavelengths is 565 nanometers, which is of course required in this experiment. We use a colorimeter because, unlike our spectrophotometers, it can be directly connected to the LabQuest 2, which therefore allows absorbance versus time data to be collected automatically. A second point before we get to the lab is related to the concentration of the reactants at the time of mixing. Note that because the final volume of the reaction mixture is 20 mils, both the crystal violet and the sodium hydroxide are diluted twofold from the original stock solution concentrations. This fact will be important as you present and process your experimental data. In the LabQuest is set to collect data for 180 seconds at a rate of 0.2 samples per second. This means one data point is measured every 5 seconds. Scott rinses a cuvette with 0.1 molar sodium hydroxide and then fills the cuvette 3/4 full with this solution. The cuvette is placed in the receptacle, the lid is slid closed, the 565 nanometer wavelength is chosen, and then the colorimeter is zeroed by pressing the Cal button. Using a graduated cylinder, Scott measures 10 mils of the 0.1 molar sodium hydroxide solution. In a similar manner, he measures 10 mils of the crystal violet solution. And then transfers it to the reaction beaker. The temperature of the solution is measured and recorded. The reaction is initiated by pouring 10 mils of the 0.1 molar sodium hydroxide solution into the reaction beaker. The cuvette is quickly rinsed with the reaction mixture, filled 3/4 full with this solution, and then placed into the colorimeter. The start button on the LabQuest 2 is tapped to begin the data collection. Here we see the LabQuest screen as the absorbance of the solution is plotted as a function of time in real time. When the data run is complete, the file is exported to a USB memory stick as a text file. After watching this video, you will be given access to a unique set of data in an Excel file. You will also have available to you an additional video which will guide you in the required data processing.